Greetings. Welcome to my first presentation on structural engineering and wood. In this first introduction, we're going to start at the very beginning and we're going to talk about wood as a living building material, very different from steel and concrete, for instance. We'll talk about defects in wood, or the natural properties of wood that could potentially lead into defects, wood grades, and the cuts of lumber. So starting at the very top, there are two different types of trees. They're broadly two different categories. They are referred to as soft or hardwood. Softwood comes from conifers or pine, and hardwoods come from deciduous trees, such as oak. And deciduous trees are here the broadleaf trees that drop their leaves in the winter. These names are a bit misleading, it points out here, as hardwoods are not necessarily hard and softwoods are not necessarily soft. So, for instance, balsa wood, which we use to make architectural models, is actually a hardwood, and it is softer than any commercial softwood, however. So a very, very soft wood, but it is actually a hardwood. And conversely, some softwoods, like a yew, are actually harder than most hardwoods. So the name in and of itself does not indicate how hard or soft the wood really is. In general, wood, the purpose of it is to conduct the water and the nutrients up to the leaves and the tissues. So the rainwater, of course, finds the roots down in the ground, and then it is taken up through the tree trunk into the leaves, where it does its work up there. Take a look at a nice cross-section of a tree trunk. So trees increase in diameter by the formation of new woody layers which envelop the entire stem, living branches, and roots. So the center of the tree is the sapling, the original sapling, the beginning of the tree, and then as it grows new layers on the outside, actually. So it occurs between the existing wood and the inner bark. So in here is where the actual growth is taking place, behind the bark there. And here's another cross section. So sapwood is the younger, most outermost wood. Okay, so out here is the newer wood that's growing, and then the heartwood on the inside is the original again. In a growing tree, the sapwood, out here, the yellow, is the living wood, and that's the part that conducts the water up from the roots to the leaves. All wood in the tree is first sapwood. The more leaves a tree bears, the more vigorous its growth, the larger volume of sapwood that is required. So the bigger trees, the big canopy of leaves, they need more sapwood to get all those nutrients and all that water up to the top. So therefore, hence, trees making rapid growth in the open have thicker sapwood for their size than trees of the same species growing in dense forests. So the more space, elbow room, so to speak, that a tree has, the more robust its growth could be, and then therefore you could conclude that the sapwood is actually it has a greater amount of sapwood than its the same species of tree growing in a dense forest where it doesn't have the room to grow. And another good diagram here, clearly making that point, that here in the beginning is the little sapling, and then it is essentially enveloped, or eventually it's all turned into heartwood. And we could see this growing over the years. And here's more secondary growth, increasing the diameter of the tree and sometimes enveloping obstructions. So a metal post or something like this could continue to be swallowed by the continued growth. And then I came across this. I'd have to assume it's a real photograph. So it enveloped this. Somebody left their bicycle, I guess, leaning against the tree, and the tree just took it over. I don't know why anybody would falsify such a wild photograph as that. And then the heartwood in the center here. And here's a section of a yew branch showing 27 annual growth rings. The pale sap and the dark, so the pale sapwood and the dark heartwood are very clear. And then the dark radial lines are small knots, and that's those, and we'll see more about those soon. So this is where the tree branches were coming out. So once heartwood formation is complete, the heartwood is dead. So all of this center wood is actually dead. It is more resistant to decay, actually. In a cross section, it appears as a circle, usually follows the growth rings in shape. So the annual rings are the growth rings. So each year a ring is added, and it's the heartwood typically follows that pattern, that exact same shape. Another view of a nice cross section of a trunk or a large branch. So the heartwood coming through the center, and then there's a branch coming off of it. So a branch coming off a branch is of course possible. And then just to go back one, so this is a longitudinal section cut in the length, along the length of the trunk, as opposed to this where it's a, so this you might not actually call a cross section. I might have well, it's a longitudinal cross section. It's definitely a cross section, but longitudinal, so running along the length of the trunk, as opposed to here is a cross section across the trunk. So it's the same, the dark wood is the same, we just cut in a different direction from one to the other. Young trees are often almost covered in limbs from top to bottom. That's what we see here. But as they grow older, some of them die and break off. Subsequent growth, the new growth, might completely conceal those stubs, will ever remain as knots. That's an important point. So no matter how smooth and clear the outside of a log is, it is more or less knotty in the middle. So this little sapling became this tree, and all these little branches eventually fell off, but buried within this trunk here are the knots. So it doesn't matter what this looks like, years later. The fact is there most likely were branches down here at a point, and they have left knots behind. Consequently, the sapwood of an old tree will be more free from knots than the inner heartwood. Okay, so this, again, the trunk of the sapling is now the heartwood within the tree here. So the heartwood here most likely has knots in it. Okay, knots are defects, and they weaken the timber and interfere with the ease of working with it, and other properties. So it follows that a given piece of sapwood, because of its position in the tree, may well be stronger than a piece of heartwood from the same tree. So the outer ring, the outer kind of circumference where the newer wood is down here, does not have branches. Therefore, it does not have knots, and therefore it's probably stronger than the inner heartwood. Another look at the annual rings, or the growth rings. So kind of interestingly, where there are clear seasons, here in Philadelphia, for instance, growth can occur in discrete annual or seasonal patterns, leaving growth rings. That's what we see here. But if you go down towards the equator, where there are no clear seasons, not the clear seasons that we have here, then you'll find trees, palm trees, for instance, without any growth rings, because it's just, I guess, one long growing season for the life of the tree. Doesn't change the way it does in colder climates. And here, this is, I find very, very interesting. So a cross section from a roof beam of an ancient Pueblo Bonito in New Mexico. So builders crafted the beam from a tree cut in AD 1070. Scientists looking at this cross section could note that there were droughts in these years, which is very, very interesting. So they could determine the age of the tree, and then they could count, and these rings kind of serve as a diary for and to the trained eye, to which seasons were robust in terms of growth and therefore being fed plenty of water versus droughts. So very interesting. And similarly, the history of the tree from over 40 years of growth. Okay, and now looking again, same view into the cross section and talking about cuts of lumber. This is very important. So how we cut lumber out of the tree and how these rings run through the piece of lumber has a big effect on its strength and really its stability, most importantly. So the premium, the best piece here is the quarter sawn. So the grain comes through at nearly 90 degrees to the face, premium lumber. So we could see how it is coming through. So this is the face in this direction, the long face right there. So if let's just say it was a 2x8, that would be the 2. This would be the 8. The 8 is considered the face, and the rings are coming through perpendicular to the face, nearly perpendicular, very stable piece of lumber. The least stable is the opposite here, where the end grain is running parallel to the face. Okay, so that's flat sawn or plain sawn lumber. And we can see it right there, cut right here. And much more wood. There's only so much wood you could cut out at this true quarter sawn position. And then we get into the two cuts, the rift sawn and the combination plain and rift sawn, that are somewhere between these two. So best, weakest, and somewhere between the two. So these would be more stable than the flat sawn, less stable than the quarter sawn. This is just a view to show that when these trunks, these timbers arrive at the sawmill, the mill would have to determine the optimum way to cut it. And there's only so many, again, quality pieces that could be pulled out of this kind of jigsaw puzzle. And another view of them being cut out. So there's our quarter sawn right there, quarter sawn coming around, and here's our plain sawn or flat sawn. What do we call it here? Flat sawn. Yes, that's what I would call it, flat sawn. And some important geometry. Always when we describe structural members, be it steel or trees, whatever it is, we always have to know our vocabulary to describe things properly. So longitudinal, extending in the direction of the length of the primary axis, running lengthwise. So this is the tree trunk, and that would be the longitudinal axis of the tree, and then that's a longitudinal cut. And like I said with that other slide, I'd call that a longitudinal cross-section if we cut the tree and looked into it that way. Transverse, lying or extending across or in the cross direction. So I would call this a transverse cross-section, essentially. And you could describe a room or the building the same way. If you have a very long building and you cut a building section through it, you would have along the long axis, it would be a longitudinal building section. And then if you cut it across the shorter direction of a building, you'd call it the transverse building section. So just basic terminology for describing geometry. Array, so this goes back to perhaps high school geometry. So one of a system of straight lines emanating from a point. So that's our basic geometry definition. And here's ray right there, ray. So that is the knots, essentially. So this is the branches would radiate from here out, and those knots would be could be described kind of as rays coming out of the center of the tree. And then tangential. So touching at a single point as a tangent in relation to a curve or surface. So again, that's our high school geometry. So tangential, and do we see that word in here? Here we go, tangential section. So it's cut, so it's a longitudinal cut, but it's cut so that it is kind of just touching the edge of one of these circles, as opposed to, so here, that would be essentially a tangential section right there. This is not. This is cut perpendicular to the rings. So this would be a tangential cut. Okay? And we can see that nice and clearly here. So here's a cross section in that direction. A radial section coming right through the heart of the tree, and then the tangential sections are cut, again, just touching the circle. Just touching the circle. And this is what the tangential section would look like. These annual growth rings would kind of become these waves. And that is what that all says there. Yes. Okay, here's our nice piece of quarter sawn lumber with our rings coming through 90 degrees to the face, appearing as closely spaced parallel bars. Since there are relatively few large perfect quarter sawn boards that can be cut, they are more expensive. Boards with straight grain. The board has been cut so that the wood fiber runs up and down the length of the board. The board is cut along the length of the tree, resulting in the greatest strength of wood. So this is kind of intuitive, but it's definitely most common, right? When we go into Home Depot and we look at things in the lumber yard, this is how we know that the wood has been cut along the length of the trunk, as opposed to cutting cross sections, cross grain boards. The board has been cut across the grain. So here we are cutting with the grain. So the grain of the tree runs along with the trunk. So we are cutting along the grain here, and here we are cutting across the grain. So this results in very weak wood. The boards are rarely cut on this way on purpose. So butcher block, sometimes you'll see maybe like decorative accent walls. It's a, visually it's pretty cool, but structurally it's not really of any use. Okay, knots. Very important subject. All right, a knot is a particular type of imperfection in a piece of wood that affects the technical properties of the wood. Very important. In a longitudinally sawn plank, a knot will appear as a roughly a circular solid right there, usually darker, and then the wood grain flows around it and rejoins. So the wood grain, so this is what we call the wood grain. These kind of marks, these striations kind of running down, and they'll run down, and then they'll kind of move around the knot, kind of like water moving around an island in a river, for instance. All right, in grading lumber and in structural timber, knots are classified according to four things. Their form, which kind of their three-dimensional shape is what I would call their form. The size, the soundness of the knot itself, and then the firmness with which it's held in place. So four different things that people who grade lumber are looking at. The firmness is affected by the length of the time that the branch was dead while the attaching stem continued to grow. So kind of interesting. And knots materially affect the cracking or the checking. We will look next in our next slide. We'll start to look at some defects, which checking or cracking are defects, and warping, the ease of working with the wood, and the cleavability of the timber. They're defects which weaken the timber and lower its value for structural purposes. All right, and here's a look at the next two slides are a look at some different defects or kind of natural, well, they could be related to how it was dried, how the wood was dried. That's definitely a big part. Things often go wrong. Same with vegetables, for instance. You could cut a perfectly beautiful vegetable from a vegetable bush of some sort, and then after how it's processed and taken care of before it finally reaches the dinner plate, everything could go wrong. And the same is true of wood. You could have a fantastic piece of timber coming off of a tree, out of a tree, and then if it's not taken care of properly, manufactured and dried properly, big problems could occur. So again, this is the face, this is the cross section. So the face is the long side of the cross section right there. So if there's a 2x8, again, that would be the 8 inches. So a bow warp on the face of the board from end to end. So we're going in this direction with our bow. Or no, I'm sorry, I think we're going in this direction. So it's these crook. Yeah, so these two, the bow and the crook, are a little hard to read, actually, just kind of the way they're drawn. They kind of look the same, but basically the crook is bending about this direction here, that direction. So this line is not bending. That's a straight line, and it's bending in this direction. The bow, again, that line is straight as well, but the bow is bending here against the longer face. So in the crook, it's against this shorter face right there, and in the bow, it's against the longer face right there. or actually in this direction, bow, I'm sorry. And the crook, or the cup, I'm sorry, the cup. The cup is bending in this direction. So the cup is drawn well. We can see what the cup is. And we'll see more on that because this is the less stable of the cuts from the tree. And that is what you would expect to happen. So this is deck boards could cup because they are often this type of cut. And this is the direction that they would begin to warp in. Okay. So the bow is bowing in this direction, the crook is going in this direction. And when carpenters make walls, so we're talking about dimensional lumber framing, when they're putting up walls or putting together built up beams, for instance, a girder, and doing this all out of 2x material, they will look down at a piece of wood, they'll sight it, they call it, and they'll see which direction the crooks are running. And all the crooks in a wall would all be facing in one direction. So that way, when the drywall comes to be installed, it is not being pushed in and out. If one crook is facing the exterior house and then the stud next to it, the crook is facing the interior of the house, it's going to stress the drywall. So that is why carpenters will put all the crooks facing in the same direction. And likewise in a beam, you don't want crooks, pieces of board that have been joined together. You wouldn't want some crooks going up and some crooks going down. Basically in a beam, all crooks would go up, and in a wall, all crooks would face one direction, typically out for exterior walls. Okay. All right, splits happen. So cracks that go all the way through the piece of the wood would be a split. That's that often happens due to poor drying habits. Twists are again kind of going out of plane, and checks often follow those annual growth rings, but they do not pass through the entire piece of wood. So those are a little more straightforward, those diagrams. All right, structural framing can be determined in two different methods. One is visual inspection and the other is machine testing. So here are visual inspectors watching the pieces come by. Here are the stamps that they use. So it requires a trained and certified lumber grader. They inspect every piece. They assign a grade based on characteristics such as knots, wane, and the slope of the grain. Okay. The highest visual grade for framing lumber is select structural, and then in order 1, 2, and 3 to the bottom. So structural engineers and architects will typically say that you'll find in the notes the specifications for a building that all framing lumber must be number 2 or better, for instance. And here's some machines that are used for mechanical testing. Okay, so equipment used to measure the actual property, like stiffness or density. So we have been discussing these in the class for each piece. So this is not visual, this is an actual property. So they're pushing and pulling on these things and determining what the actual property is. So they are machine stress rated or mechanically evaluated lumber. So not used widely outside of the truss and glulam manufacturing industries. So typically our dimensional 2x4s and lumber that we find at the Home Depot have been visually graded. When we're talking about engineered lumber, it's been through this process here. Okay, big conclusion on the point of grading. So no matter what grading process is used, the lumber grade corresponds to a set of structural properties that predict how the lumber will behave in compression, tension, bending, shear, and deflection. Okay, so that's really the big moral of the story there. Okay, and finally there are, in regards to the lumber grade still, there are some design values that are applied to lumber that has been mechanically tested. And these are the numbers that engineers are most interested in. So they review the bending, and that's what these diagrams, so the underlined one is what we're looking at in this particular slide, and bending, of course. So that's what we see here happening to all of these. We see tensile failures at the first two, right? They originate at the very bottom of the beam, so those would be tensile failures. We see these two are cracking all the way through. Here, something happened. This is on the compressive face of the timber, and here we see something coming right through the middle there, maybe a shear failure perhaps. Okay, so that is bending. And then we have shear parallel to the grain. So again, very important, the grain runs in the same direction as the tree trunk. So it runs along the longitudinal axis of the timber. So shear parallel to the grain would be like this, right? The top is being pushed that way, the bottom is being pushed that way, and the two are pushed past each other. So that is shear parallel to the grain. Compression perpendicular to the grain. So the grain runs this way, and here is compression. So there's an arrow on the other side of this. We can't see through the trunk or through the tree, through the timber, pushing up. So two arrows facing each other, compression perpendicular to the grain. Grain runs this way, the pushing is coming in perpendicular to it. Compression parallel to the grain. So here the grain is running up and down, and we know two arrows facing each other is compression. So here are some posts or columns that have been crushed in compression parallel to the grain. And finally, tension parallel to the grain. So same as the slide before. Here they're pushing in and crushing. Here they're pulling apart and tearing. Okay, and just different ways relative to the grain that the tearing or the crushing could happen. And the modulus of elasticity, I couldn't really find a picture that expressed that very clearly, but we know that that is a measure of its stiffness, of course, and that is found on the stress-strain curve in the elastic region. So that is a measure of kind of the deflection as we walk the floor, and the joists are kind of bouncing a little bit. That is the stiffness, and of course some bouncing, a little bit of deflection is allowed. Typically you wouldn't feel it, of course, in a new house. I happen to live in a very old house, and you could feel a little bit of softness maybe under your step, but again, a measure of stiffness in the elastic portion of the stress-strain curve. So the elastic portion is when everything is okay and it just deflects a little bit and then it bounces back. Okay, thank you.